This tutorial will walk you through an example of simulating loaded shell or plate structures in Abaqus. We will load a flat plate in a direction perpendicular to its planar surface so that it undergoes bending. One edge of the plate is fixed so that it cannot translate or rotate about any axis. Two concentrated forces of 7,000 newtons each are applied at 2 points on the opposite edge. The plate will be partitioned twice, and the 2 points where the partition lines meet the edge can then be used to apply the concentrated forces. The dimensions of the plate are displayed in the schematic. The units are in SI with length in meters. The plate is 0.1 meters or 10 centimeters thick. It is made of steel with a density of 7.8 grams per centimeter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.3. We will talk about some aspects of shell simulations that you need to understand, such as section integration and whether it needs to be performed before or during the analysis. We will see how to apply shell thickness as a section property and briefly talk about the Simpson and Gauss thickness integration rules. We will also talk about shell offsets. We will assume this problem is mildly nonlinear. Initially, when the plate is flat and just beginning to bend, it will have bending stiffness. However, after it has bent a little bit, some of the bending will also be resisted by in-plane membrane effects. Hence, Abaqus needs to update the stiffness matrix to include the added membrane stiffness. This makes our problem a geometrically nonlinear one, and we'll use the nonlinear geometry or NLGEOM option. So open up a new model in Abaqus and let's do this. Let's open up a new file in Abaqus. We'll rename the model Plate Bending Model. Let's create a new part. We'll name it Plate and we'll set it to type 3D deformable. We're going to set the base feature to shell. Now base feature shape literally refers to the shape of the part that we'll be creating. It doesn't refer to the type of analysis we'll be performing. In previous tutorials, we've selected point and wire, and you know that there's no such thing as a wire element or a point element. Similarly, when we select shell, we're only telling Abaqus that our part is going to be in the shape of a shell. We're not telling it that we'll be meshing it with shell elements and doing a shell analysis on it. This is useful because when Abaqus knows we're creating a shell-shaped part, it's going to give us the options that are useful to us when creating a shell, or maybe not give us options that wouldn't be useful when creating a shell. For example, if you selected solid, after you sketched it out, Abaqus would prompt you to extrude it and give it some depth. Whereas if we go with shell, once we sketch it, Abaqus knows that this is a shell, so it's not going to tell us to extrude it. As for the type, we're going to set that to planar because we're creating a plate, which, as you know, is a planar object. We'll set the approximate size to 20 and click on Continue. You find yourself in the sketcher. Let's use the Create Lines Rectangle tool. This will allow us to create a sketch of the plate. Abaqus prompts you to pick a starting corner for the rectangle, and then to pick the opposite corner. Next, we'll use the Add Dimension tool to dimension our plate. Once we're done sketching the section for the planar shell, we can click the Done button. Create the steel material as you've done in the previous tutorials. create a new section called Plate Section. Set the category to Shell. Abaqus offers you many different types of shells. You need to pick the correct one depending on the type of analysis you're performing. If, for example, your shell consisted of many layers of materials, you'd go with the composite type. On the other hand, if your shell was like a membrane, where it has strength in the plane of the surface, but no bending stiffness, then you'd go with the membrane type. In our case, we're going to go with homogeneous. The homogeneous type has stiffness in the plane of the surface and also has bending stiffness. Abaqus will allow you to specify the thickness of a homogeneous type shell. Click on Continue. You see the Edit Section window. Abaqus asks you whether to perform the section integration during the analysis or before it. You've seen this before if you think back to the beam frame example. If we know that the response of the shell is going to be linear elastic, and we're also not going to consider temperature or predefined field variables in this analysis, you can choose before analysis. On the other hand, if you're expecting nonlinear behavior, or you plan to account for heat transfer, you need to go with during analysis. If you choose that option, Abaqus will calculate the section properties by numerically integrating through the thickness of the shell during the analysis. We're going to go with this option. Abaqus needs to know what the thickness of the shell will be. We know that our shell will have a uniform thickness of 0.1 meters, so we'll specify a value of 0.1. If you had a shell with variable thickness, you could go with element distribution or nodal distribution, and that would allow you to specify a spatially varying thickness for your shell using a distribution. We make sure that the material is set to steel. Next, we need to set the thickness integration rule. A moment ago, we decided that we would go with during analysis for the section integration. In order to numerically integrate over the section, Abaqus gives you two methods. They are Simpson and Gauss. The Simpson integration rule should be used if you would like results to be output on the shell surface. If you're using a composite shell, the Simpson integration rule will allow you to find the transverse shear stresses at the interface between two layers. Also, the Simpson rule must be used for heat transfer. On the other hand, Gauss quadrature should be used in cases where you don't care about the results on the shell surface. Gauss quadrature cannot be used for coupled temperature displacement or for heat transfer. By default, Simpson rule uses 5 section points for a homogeneous section, whereas Gauss quadrature uses 3 section points. You see the default value of 5 displayed for thickness integration points. We're going to leave that at this default. Next, we assign the section to the plate. In the Edit Section assignment window, Abaqus asks you to specify a shell offset. Let me explain what this means. When you use shell elements, they're created as a surface called the reference surface, and this reference surface is where the nodes of the shell elements are. In reality, of course, shells have a certain thickness, so what you usually do is you specify the reference surface to correspond to the middle of the actual physical shell surface and specify a thickness. And this represents your shell in the analysis. However, sometimes when you import a model from CAD, you find that the CAD modeler has represented either the outer surface or the inner surface of the shell as part of the CAD model. And it would be incorrect to put the shell elements on this surface. So what you do is you tell Abaqus to offset the reference surface from this surface. And you can do this by selecting one of the shell offset options. You can go with top surface, bottom surface, or middle surface. In fact, you also have the option to specify a value. This value would need to be a fraction of the shell's thickness from the shell's mid-surface to the reference surface. For example, if you set it to 0.5, the top surface of the shell would be the reference surface. If you set it to -0.5, the bottom surface of the shell would be this reference surface. In our case, we're going to select middle surface. Click on OK. Next, let's create the assembly. We'll import the plate as a dependent instance type. Then we'll create the step. Let's call it load step. We'll set the procedure type to static general. Let's turn on nonlinear geometry, or NLGEOM. This is because we can expect some nonlinear behavior in the simulation. Initially, the plate is only going to have bending stiffness, but once it's bent a little bit, we're going to experience membrane effects, or membrane stresses, which might increase the bending stiffness of the plate. We'll rename the field output, calling it output stresses and displacements, and we'll set it to output exactly what the name suggests. We're not going to request any history outputs for the simulation. In fact, we'll delete the pre-existing one. Right-click on HOutput1 and choose Delete. While you're probably unlikely to do that in any of your actual simulations, I just want you to see that it's possible. Let's create the boundary condition. We'll call it Fix Edge and apply it in the initial step. We'll set it to type displacement rotation in the mechanical category. Let's check off all the translations and all the rotations as well. This is going to fix the left edge of the plate. In previous tutorials, when we wanted to fix an edge, we used the Incaster boundary condition. Incaster does the exact same thing we just did. It basically constrains the rotations as well as the translations. So you could have used that instead. I'm just showing you a different method of achieving the same thing. We wish to apply concentrated forces at 2 points on the right edge of the plate. However, it isn't possible to select 2 points on this edge the way that it currently is. So what we're going to do is create 2 partitions. The partitions are going to lie along the length of the plate. The points at which the partition lines meet the right edge of the plate will become selectable nodes. In order to create the partition lines, we're first going to create 4 datum points. We'll use the Create Datum Point Enter Coordinates tool. We'll type in the coordinates of the datum points when prompted by Abaqus to do so. Now let's use the tool called partition face. Use shortest path between 2 points. We select the start point and then the end point to create one partition. Then click the Create Partition button. Now that you've created one partition, you've got 2 faces, so Abaqus needs to know which face you plan to partition next. So choose the lower face and then click Done. You can now partition this face by selecting the next 2 points. Now let's apply our concentrated forces at the newly created nodes on the right edge. Next, let's mesh the plate. We can assume that the strains in the plate will be small. Hence we're going to go with quadratic shell elements because they give good results for thin shells with small strain. We'll seed the edges of the plate by number. We'll assign 3 elements to each segment of the shorter sides. This means we'll have 9 elements on the left edge and the right edge. We'll assign 10 elements to the horizontal edges. Notice that I selected all of the partitions while doing this. We then tell Abaqus to go ahead and mesh the part. Now that the setup is complete, let's create and run the job. Since we did not specify history outputs, and in fact deleted the pre-existing one, Abaqus warns us that no history output has been requested in the load step. We're going to tell Abaqus to continue with the job submission by selecting Yes. Once the analysis has completed running, right-click on Plate Job and choose Results to view the visualization module. We're going to tell the Abaqus viewer to display element labels by going to the Common Plot Options tool and checking off Show Element Labels in the Labels tab. We can plot our field output as contours by using the Plot Contours tool. By default, Abaqus will plot the mesostress. We can write these to a report by going to Field Output in the Report menu. We'll check off mesostresses. In the Setup tab, we can give our report file a name, and we'll uncheck the Append to File option. We'll tell Abaqus to sort the table by mesostresses in the descending order. We'll also tell Abaqus to write out the column totals and the minimum and maximum values in the column. Since I've performed the simulation once before, Abaqus warns me that this file already exists and it's going to be overwritten since we unchecked the append to file option. You probably won't get this warning message if you haven't performed the simulation before. I'm going to click yes. Notice that the report file has been created in my Abaqus working directory. I've set my working directory to Abaqus temp in the C drive, but yours might be different. By default, it's likely to be the temp directory in the C drive. I'm going to open up this report file. Notice that one of the columns is the element label. This is why I made you plot the element labels on the plate before. You can now tell what the stresses are on each of those elements. Abaqus has also written the minimum, maximum, and total values at the bottom of each column since we checked off those options. And that concludes this tutorial.